That's what I want. So what's this option here? Okay, let's turn in the homework. I think I want to do numbers 12 and 14, if that's okay. We'll talk about 12 and 14. I've posted the written homework for a week from today, so if you want to get started on that, there will be then a short reading assignment for Friday. That will be posted later today. Okay.
In the slot, I got a bit of
Okay, so the homework page, here we go. So number 12 was about the U.S. population. It said it was 273.6 million in 1996, and it increased approximately 1.1% each year. Okay, and so we want to analyze the situation. So there's kind of two main ways to think about exponential growth. So what is one of the ways we can think about exponential growth? What characterizes this type of growth? There's two ways to think about it. Multiplication. Okay, what's the multiplier called? The growth factor. And is the multiplier, do we multiply it times the output or times the input? Times the output, and it gives us the next output. The next output, okay? So the other way to think about it besides growth factor, multiplying by the growth factor, that's key. That's kind of how we started with exponential functions. But now with your reading for Monday, we saw, and then when we did Monday, we saw there's kind of a slightly different way to look at it, which is what? Yeah, percent change, exactly. So what is our percent increase here? 1.1%. So this percent increase and this growth factor go hand in hand. They're inseparable. So we want to really make sure we know how to go back and forth between those really well. So if we have the percent increase, to get the growth factor, the growth factor is always 1, either plus or minus the change. That's how we're always going to think about growth factor. It's either 1 plus or minus the change. Okay? So is this going to be plus or minus? This is the population is growing, so plus. So then if we got 1.1%, what is that as a decimal? 0.011. So there's our growth factor, 1.011. What does the 1 represent? What you had before. That's what you had before. And then the 0.011 is the amount of change. And so that corresponds, that 0.011 corresponds right along with the 1.1%. Okay, so there's our growth factor. So how can I get the population then 1 year later? Based on our idea of exponential growth, how can I get this next population? That's it. So I can just take the population from before and multiply it by 1.011. How can I get the next year? Okay, and where does that come from? So here's the year before. What do I do to the year before to get the next year's population? No, the year before. The year before. How do I get the next year's population from the previous year's? Multiplying it by 0.011. That's right. Okay? So if I were to skip down, you just imagine that process continuing. Say I skip down 3, 4, 5 to the 6th year. Okay? By then, by the 6th year, what will we have done following this pattern to get to that population? We will have started with the 273.6, and every year multiplied by the 0.011, so that at the 6th year, how many times will we have multiplied by 1.011? 6 times, once for every year. But now we don't want to type that out. So multiplying that same number together 6 times is, this is where exponents come in, exponential growth. It comes in because an exponent represents, what does it represent? Repeated multiplication, repeated multiplication. So exponential growth is exponential because that exponent represents the repeated multiplication of the growth factor. So now in the xth year, so now any number of years, we're going to start with the 273.6, and for every year that goes by, we're going to multiply 1.011. So how many of those? X of them, right? X of them. So our input becomes the exponent because it's the number of times we repeat the multiplication. That's the input. The number of years that go by is the number of times that we repeat the multiplication. So that's our function. So they told us to call it f. So f of x equals this. 273.6 times 1.011 to the x. So when you see a function like this, your image in your mind of what's happening in that function should be this thing. Every time you advance to the next output, you multiply by another 1.011. So if you advance forward from the starting point, if you advance forward x number of inputs, you're going to multiply by that number of growth factors to get there, to get that value. Okay. Doesn't make sense. So it asks for approximate population in 2010. So we can look at that in 2 ways. We can just use the function, or we can think about what it would mean in the pattern to get to the year 2010. But they're both kind of the same thing if you understand the function. Okay? So 2010, if we're starting in 1996, would be what? Is that 14 years since 1996? Okay, so 273. So by the 14th year, we will have multiplied by every year for 14 years, we multiply by 1.011. So imagine 273.6 times 1.011 times 1.011 times 1.011, 14 times, once for every year. So that's how that function works, because when you plug 14 into this, that's what you get. You get 273.6 times that thing multiplied together 14 times. So f of 14 is just exactly that thing that we wrote over here. Okay, does it make sense? So really important that you just don't get into kind of equation mode, formula mode, but you really have an image of what's going on there. Okay? Because then when you come to a new situation involving exponential growth or an exponential equation, and it's kind of a new question, something that's unfamiliar. If you have an image and your understanding of what that is, then you can tackle the problem. Okay, you can tackle the problem. If you just have a mentality of I know how to plug in X and crank out Y's, then anything different you won't know what to do. Okay. So your understanding gives you versatility, right? To be able to tackle lots of different problems. That's why we focus on that. Okay, and then it asks, in what year will the population reach 400 million people? So what we're saying now is that the output, or the output of the function is 400 million, and we want to know in what year that occurs. Okay, so we want to, we want to do that graphically at this point. So what was our function? Y equals 273.6 times 1.011 to the x. Okay? Nothing shows up. Why not? What is the initial value of y here when x is 0? And what am I showing? I'm showing 0 to 7. So I'm going to zoom out on the y-axis. Is that right? Until I can see.
Wouldn't you have to plug something into y2?
What's that? Oh, I just want to see the graph for now. Oh, yeah, we'll get there. Yeah, we'll get there. So here we go. And let's specify that this is just for after 1996. So I'm going to say x is greater than 0. So, constant rate of change? Is it constant rate of change? Yes or no?
Yes.
I'm saying yes.
It looks like it appears.
It appears because what is constant rate of change?
It's a linear
Straight line, right? And that constant rate of change is based on, for every change in x, you have, and it stays the same, right? It stays constant. This change in y stays constant. What do we think? True? Constant change in y for change in x? Some are saying no, some are saying yes. What kind of growth do we have? Exponential growth. And that means that the percent change stays the same. If the percent change stays the same, that means we increase by a certain percent, and then we take that amount, and we increase by the same percent. And then we take that amount, and we increase by the same percent. Is it constant rate of change? No, because the amount of change does what? It goes up, right? The amount of change, if the percent stays the same, you're taking the percent of a greater and greater number, the same percent of a higher and higher number, then that change is going to increase, right? That change is going to increase, yeah.
So for exponential growth, you're never going to have a constant speed.
Constant rate of change, absolutely, right? It's a different kind of rate of change. It's one type of changing rate of change. Yeah, so constant rate of change, we know as graphs as a line. Changes in y are proportional to changes in x. What's that? Compounding has to do with, when you have a percent that stays the same, you keep adding on to
the previous.
You take the same percent of a new higher and higher amount, right? So that amount of change increases. Yeah. So now it asks for in what year we would hit what population? 400 million. So I think this gentleman over here wanted to look at let's just. There's a pretty good picture of it. So now I'm showing this is our growth of the population, and then this is showing y is 400, population's 400. So what about this is going to help me find the year that we hit population 400 million? How does that help me find? So what about this illustration right now gives me the year? The y. Is it the y? So we really got to, when we're looking at a graph, we really got to know what our two quantities are. The x quantity is? This is the years since the 1996. Okay? And y is? That's our population, right? What's growing exponentially? Input or output? Output. How is output represented on a graph? Y. Output. The population, or the y value, is what's growing exponentially. That's why the growth factor is always multiplied by the output, because that's the thing that's growing exponentially. So this pair right here is 34.72 and 400, telling me that 34.72 years since 1996, we hit a population of 400.
So you just plug that into your graphic calculator?
Yeah, so you want it, so graph this on the graphing calculator, and then I also graphed y equals 400, and then I'm looking for that intersection.
What about like in the series the logs and the original?
Yeah, so we haven't done that yet. So that's at the end of this module. So what we've got so far is to do it graphically.
So will we still get it right on the homework by today using the natural law?
Yeah, sure. Okay. Other questions about this problem? So let's look at number 14, which is our first. You read about decay, but here's our first in-class example. So it says that in this decay problem, the initial value of the car is 25,000, and then it depreciates by 14.5% each year. Okay, so this is the idea of exponential decrease or decay. And so it says it's going down 14.5% each year. Okay, so this is our percent change. We want to find the growth factor. That's the key to all these. Again, the growth factor is going to be what you had before plus or minus the change. So we're going to have plus or minus? Minus how much change? 0.145. So get in the habit of, this will really help. Always write the growth factor as either, write it up here, growth factor, either 1 plus p or 1 minus, or, you know, if the p is positive, that's growth. If p is negative, it's decay. So get in the habit of writing your growth factor as 1 plus p or 1 minus p. Okay? So what is that growth factor? 0.855. And so every year the car is going down by 85.5%. Is that right? No, it's going down by 14.5%. Okay, so in this context, what does the 0.855 mean? This the decay factor, the multiplier. This is what we're going to multiply by every time. Is that the percent change? So the car changes value by 85.5%?
No, it's saying after 1 year the car is worth 85.5% of its original value.
Which one? So is it the percent change or the amount of the original value that it's worth? Yeah, so we want to think of the decay factor as kind of like what we keep when we move on. So when we move on to the next year, it's the fraction or the portion of our previous amount that we keep. That's the key to the decay factor.
When we move on in years.
When you whatever the input is, when you move 1 unit of input, if you move 1 unit of input, your output you're going to keep this fraction of the output, and therefore it's going to go down how much? It's being decreased by this much, by 14.5%. So our decay factor represents the portion that remains, that we hold on to, that we keep. All right, but everything else works the same now. Once we understand how the growth factor works and what it means, how are we going to get after 1 year? What's going to be the value? How can we calculate the car's value after 1 year? 25,000. That's it. Multiply by the 0.855. Same thing. And then the next year, we can take the previous year, which is the 25,000 times 0.855, and do what? Repeated multiplication of the growth factor. That's what this is about. Or, so that's the one way to think about it. Or the other thing is, every year, what happens? That means if we're keeping 85.5% every year, the percent change every year is going down 14.5%. So, after n years, you think about this, we would start at 25,000, and we would keep going through this process. It would be decaying exponentially. So after n years, what would the car be worth? 25,000 times? Yeah. N by this time in years, we will have multiplied by 0.855 n times. Imagine 0.855 times 0.855 times 0.855, n of them. That's where the exponent comes in, just to make our life easier than having to list out that same number lots of times. So that's our function. So we can call this one g of n, say. G of n equals 25k times 0.855 to the n.
Would it have been wrong if you just did 25 3 zeros without making the decay there?
What does the k mean?
Yeah,
Yeah. So we really want to understand things. So different notations are less important. Yeah.
we wouldn't get marked off
I'm just saving some room here. Just saving some room. Okay, so when will the value of the car be less than 1,000? So what do we expect a graph like this? So we've got exponential. First of all, it's exponential. So will it be a line? Nope. Will it? And then what will it look like? If it's going curved down. That's right, curved down. What's our function here? 25,000. So can I just do 25 times okay, can't see it. Oh, there it is. Just need it. Here's our car depreciating. What is the value of the car, X or Y? X. X is the value of the car. So to interpret a graph, we got to be confident about what quantities we're showing on each axis. Which is the value of the car, X or Y? Y is the output. Output's the value of the car. X represents number of years since new. That's the input. So when will it be below 1,000? So I'm going to make y equal to 1 because I'm doing it in thousands. There we go. So I got the ordered pair 20.55. And 1. What does it mean? Tell the person next to you. What does that ordered pair mean? Tell the person next to you. Go. So, volunteer. What does it mean? Anybody? Yeah. Yep. After that many years, value equals 1,000. So actually, after this, the value will be less than 1,000, right? And that's what they wanted. So somewhere in the 20th year, the value hits 1,000, and then after that, the value is below 1,000. Okay, so let's go back to number 3, and let's just have you, now that we've talked about growth and decay, let's take a look. Instead of creating the functions, we'll start with the function. So
in future homework, you just go ahead and assume you use the graphic calculator?
It depends. It depends on what we're doing. But not knowing anything else here, so plugging y in for 1 would require solving for an exponent, which we haven't done, right? So we haven't done that yet. So one method of getting that would be this graphical method.
It makes sense. It makes sense. But I think when I was doing the homework, I didn't even occur to me, and I just kind of.
Oh, so you did trial and error? Sure, that's fine too. Yeah, it's good. So you took for many years, you figured out kind of what it was, and then yeah, that's great too. Yeah. Okay, so here's from number 3. What I want you to do is answer 3 questions for each of these. The first question is, is it growth or decay? There we go. Okay, and f of n is 120 times 3 to the n. And then g of n is? What?
It's for f of n subtraction.
Okay, so 3 questions for each one. So 3 functions, 3 questions for each. First question is it growth or decay? Okay, you're gonna talk amongst yourself. You're gonna do all 3, right? So there's 9 questions to answer here. So for each one of these, is it growth or decay? And then what is the growth or decay factor? And what's the percent change? Okay, those 3 questions. Is it growth or decay? What's the growth or decay factor? And then what's the corresponding percent change? Get a partner. Take about 2 minutes to answer those questions. Go. What's that? Okay, let's see how you did. H of n, growth or decay? Growth. What's the growth factor?
1.45.
Growth factor, 1.45. Okay, and let's just practice. So even though some of these are easy, it's a really good idea to practice rewriting your growth factor as what? 1 plus. In this case, so this one's real easy, but it's just a good habit to get into. So then you can easily see what is your percent increase. What is it? 45%. So the 1 represents keeping what you had before. This represents the 45% growth. Okay? This one. Growth or decay? Growth factor equals? Rewrite it as? Yeah, so this is like an example of one that's harder to see. What percent change do you have when you are tripling? That's what this is doing. Every output is tripled. Yeah, so that's a good example of where it helps to do the 1 plus.
Because you already have the 100%.
This is from before, and then if you're tripling, you're including 2 more, right? 2 more, so that's the 200% increase. Okay? Growth or decay? Decay. Decay factor is 0.9. Rewrite it as, oh my goodness, what happened? Okay, rewrite it as 1. So we're saying 0.9 is the same as 1 minus what value? 0.1. So the percent change is? Yeah, so down, so you could say it's decreasing 10%, or we could say negative 10%. So then what, as a decay factor, what does that 0.9 represent? what you have left, or
90% of the original.
90% of the original value. That's what we're keeping every time. So what remains each, as the input advances, we always have 90% of what we had before, which is a decrease in 10%. Okay, so now for Monday, I had you, this past Monday, you did worksheet 3, and I would guess that many of you have some incorrect answers on that, because we hadn't really gotten this far yet. Something to think about. So I want to go back to worksheet 3, which is on page. Thank you, 143. And we want to review the work that you did on page 143 and 144. See if you can find your mistakes, wrong thinking, and correct it. And then you can compare with each other too. You can work together. So you're kind of redoing 143. I would guess that there's many wrong answers out there on page 143. Okay, next. So here we got these tables. So the tables I made before were vertical. These are just horizontal. Okay, so decay or growth. This should have been your image. What number do I multiply by each time to get the next output? That should have been your image of this. So how do I get the number I would multiply 108 by that would give me 36? Yeah, it'd be 36 over 108 would be the number that you multiply 108 by to get 36. And what is that? 1/3? So if this is exponential growth, then 36 times 1/3 should be 12. And 12 times 1/3 should be 4, because that decay factor cannot change. If it changes, it's not exponential growth, it's something else. Okay? It's got to be the same multiplier. Does it work? Okay, so our decay factor is 1/3. So what's the percent change? Write it as 1 minus 2/3. What percent is that?
6.6. Wouldn't it be 1/3?
What's that?
Wouldn't it be 1 minus 1/3?
No, because the decay factor is 1/3. We write it as 1 minus, how much does it go down? If we're holding on to 1/3, it means it's going down 2/3. Yep. Questions on this one?
What if you round it up to 67%?
Okay, because I just rounded to a different place, right? Because this is 6 forever, right? So I just rounded to a different place. Okay, graphs. So interpreting graphs, again, what gets multiplied by the growth factor?
Initial. Well, the last output.
Output, right? So if we want to make the same analysis given a graph, what's growing exponentially, x or y? The output, y. So if it helps, you can just recreate a table, just like we've been doing. Or you're thinking of what number multiplied by 20 gives me 32. And it should be the same number that multiplied by 32 gives me 51.2. What is it? 1.6? Percent increase. 60% increase. 60% increase. Okay, same thing here. So y is the output. We know that that's what's getting. What number do I multiply 30 by to get 12? That should be the same number I multiply 12 by to get 4.8. So how would I find this number that I multiply 30 by to get 12? 12 divided by 30. That's right. Is that 0.4? So 0.4 is the decay factor. Percent decrease. Rewrite the decay factor as 1 minus what? 0.6. That's how much our decrease is. 60% decrease. Okay, initial value. So they gave us, the first one was 30. Initial value corresponds to the input being 0, always. Always 0. So we don't know what this initial value is. Call it A. How can we use this multiplicative reasoning to solve for A? We're saying that A times what would give me 30? A times what gives me 30? 0.4. Okay, because A is the previous amount. So if I took A times 0.04, it would give me the next output. So A times 0.4 equals 30. Therefore, A is 30 over 0.4. The initial value is, what is that? 75?